So I guess we are ready to start soon. So I have a pleasure to introduce Rich Wolski. He's a professor at Santa Barbara in UCSB. And he'll be talking about statistical virtualization, scale as a tool for implementing service overlays. When Rich Wolski is, I think, a systems guy with a little bit touch of scientific computing. And he used to work in various places, right? You work at Loris Livermore, and I guess you met a lot of Googlers there. Yes. And then University of Tennessee, San Diego, yep. Supercomputing Center, and UCSD. And then we had pleasure to get him at Santa Barbara. So he's there for the last couple of years. So Rich.
Thank you, Zoran. Thank you very much. And thank you all very much for coming to listen to me speak to you today. I wanted to talk a little bit about, or I'm prepared to talk a little bit about, some work that's been going on in my group that has really been focused on the scientific computing community, which ordinarily doesn't evoke a sense of familiarity when you think about sort of large-scale computing in the commercial sector, but which I think at the end, I hope, I can show you really has a lot to do with what it is that I think that you guys do on a daily basis. And that's kind of a surprise for us. For HPC people who are used to working with tightly coupled parallel machines, the idea that large-scale distributed computing has something really important to say in terms of performance of these scientific codes is kind of novel. So that's my goal today. OK, so this is a slide that I have blatantly ripped off from San Diego Supercomputer Center, and it's very colorful. And really, all it says is that in addition to the fabulous work that goes on here, American competitiveness depends in large part on the ability to do very large-scale computations for science and engineering, right? And you can think of that in terms of like parallel computing, where you have a single machine that is capable of very fast communication and large-scale computing. But increasingly, we're starting to think about it in terms of national-scale computing. And there's a very, very unfortunate term that the National Science Foundation has coined called cyber infrastructure. I think it's unfortunate because it's not really evocative of what's going on. But if you hear that term, that's what is really going on, is the National Science Foundation is interested in trying to figure out how to use national scale computational infrastructure to forward science and engineering. At the moment, in terms of scale and topography, if you will, we're talking about something like thousands to tens of thousands of processors. But those processors are often located in clusters or very tightly coupled machines. And a variety of networks, high bandwidth networks within machines, sometimes high bandwidth networks between machines, but very high latency, low latency within the interconnect, parallel disk systems, clusters, which are commodity machines that are linked together with commodity networking typically, are popular, and they're very, very common in research settings. But the computation to communication ratio, which is really a critical factor in doing large-scale high-performance computing, is often insufficient to support some of these scientific domains. And so for that reason, you tend to buy, or there are a certain population of these large-scale machines costing from between $50 and $150 million at the moment. And they're between $2 and $10 million to run. Right? So if you buy one of these things and you put it in your machine room and you pay for the power and the lights and the security and so on and so forth, you're looking at that kind of an expenditure. And really, hard scientists, chemists, physicists, biologists, other than computer scientists, don't have the expertise or the interest or the resources to run these machines. Right? These become scientific instruments that they want to use, but they don't want to maintain. And so in a computer science setting, we think of that as the mainframe model, right? Which is there's one machine, an instrument, and it's expensive, and it's going to be shared between a large number of users. And each user, a scientist, is given an allocation, some right to occupy the instrument for a while. And from an economic perspective, if you're trying to do something like account for that, especially in a scientific context, what that means is that utilization is your measure of utility. You want the resource to be as utilized as possible. Downtime is bad. But then you also look to see where utilization is missing, and often will, in my estimation, mistakenly interpret that missing utilization for a lack of utility. And this, as I will talk about later, is a problem, I believe. Another feature of the mainframe model is that the administrators of the resource make policy. And that's because there is a large cadre of users who have diverse needs, and those needs must be balanced. They have often conflicting concerns, and you really want to make sure that the resource is heavily utilized. So this is not a very egalitarian approach. And it's also an old approach, right? I mean, basically, this has been around since the mid-'60s. It's kind of shocking that that's where we are. OK, but we are making progress. And with the very, very good networks that are available nationally at the moment, you can think about aggregating these resources to do things that are larger or faster than you can do in any one spot. But it's a little tricky. It's not a commodities game, right? I mean, Google does this a lot. There are lots and lots of machines that you have, and there are lots of places, and you manage them dynamically behind the scenes. But in some sense, they're commoditized. And for this kind of work, you can't really commoditize things because the computation to communication ratio drives the way that the program is written. And writing multiple copies or dynamically reconfigurable copies of those programs is very difficult, especially for chemists. So it's not a commodities game. And while you can buy lots and lots of bandwidth, you can't buy less and less latency. So at some point, your program becomes so tightly coupled that no matter how much bandwidth you're willing to put in one spot, if the latency is not low enough, it will run inefficiently, right? And a third feature of this is that legacy support is critical. These codes, which are often hundreds of thousands of lines, are written over the course of many decades. And the intellectual impetus for that has graduated and moved on many times over. So you can't rewrite, right? And there are many man-years of effort that sometimes go into these codes and verifying that the science in the codes is correct or whatever. So you're stuck with things that have a very long life cycle that have to run in this environment. So it's a challenging environment. And the approach that's been tried, and I'm going to try to argue that this is the wrong approach, or that we've discovered at least that it may be partially wrong, but the approach that's been tried is we call middleware. And the idea here is to say, OK, well, each of these machines has some sort of local software environment, and we're going to put a veneer that everybody is going to install at the correct rev level in a way that's compatible over the top of it, and that users can embed their legacies within a workflow, sort of a higher level program that stitches together these components. Okay, so that's kind of where we're hoping to go. Drilling down a little bit, though, each of these machines is space shared. Right? And what that means is that, like scientific instruments, users queue up to get a piece of the instrument dedicated to them. Okay? But for various reasons we'll talk about, this queue is not managed first come, first serve. Absolutely not. So we're really talking about a bunch of very, very expensive resources that individual users can queue automatically using software tools to take advantage of. And there's a scheduler that sits in between in this queue and these running jobs. These are jobs. And when the jobs evacuate, jobs are selected from the queue and allowed to occupy pieces of the resource in a dedicated way. So one of the questions that immediately comes up if you're a user of one of these systems is, how long will my job wait? Now, this sounds like an easy problem, right? It's a queuing system. We're good at queuing systems, right? And furthermore, the jobs have very well understood characteristics. You know how many nodes they need. You know how long they run for. You know what their input sizes are. You know what their output sizes are. They don't vary very much. It's not an interactive program. It's a set of ordinary differential equations that has the same size arrays pretty much every time you run it. So you think, wow, we can solve this problem by running an online simulation or by doing some queuing theory, a la Kleinrock or whatever. And it turns out you can't. You just can't. And people have tried for 25 years. Right? When I was at Livermore in the mid-'80s, before I even worked with Sergej Mitrovic on high-performance functional languages, I worked on this problem. Right? And there's a lot of efforts. There are commercial solutions that you can buy. They don't work very well. When you buy a queuing system from one of the commercial manufacturers, it usually has a prediction technique built into it. Almost all the sites turn it off because a bad answer is worse than no answer at all. If you lie to the users about how long things are going to take, they get really, really angry. So it's there, but no one uses it. It's just a hard, hard problem. Here's why. This is a trace of job wait times measured in seconds for a year and a half from a NSF-funded supercomputer in the premium service queue. Okay, the way you read this is time runs along the x-axis, and the amount of time in seconds is the height of the blue dot. So I think there's 35,000 blue dots. And each one of these tick marks, which you can almost see, is a month. Okay? This is 7 orders of magnitude variation. 7 orders of magnitude. That is a tremendous amount of variance. Okay? And this is the premium service queue. I actually used to put, I've given this slide in a number of different contexts. I used to put the name of the machine and what the service queue name was on there. And some people from this center got very angry because they said, Rich, you're making us look bad, right? You can't tell people that this is the good news. Okay? I can tell you, I just won't tell you where it's the good news. This is typical. And in fact, this is a very well-managed machine. Right? I showed you the best graph I could find from production, recent production. If you look at older graphs, if you look at graphs on poorly managed machines, they are worse than this. So you're now going to make a statistical prediction from distributions that vary over 7 orders of magnitude. In terms of days, 30 seconds or 3 weeks. That's pretty much the scale we're dealing with. Okay, that's a hard prediction problem. And that's why batch queue prediction. I can explain why there's so much variation in some regards. But before I do, let me tell you a little bit about how we came to this problem. So I've been working on this for a while. My first job at San Diego in 1994 was to solve this problem, and I didn't. But I didn't because I was sort of following what it was that the community did. And what the community does is it works with something called expectation. Now, we're going to get a little statistical here. I promise I won't get too statistical. But expectation is kind of a misnomer, right? The expected value is the value in a collection of values that you could replace all the values with and still get a similar aggregate measure, right? It's not the value you expect to happen next. And I'll give you an example of why that is. Let's imagine that we have 100 jobs varying through 7 orders of magnitude, right? 95 of those jobs wait 10 seconds or less. One job waits 1,000 seconds. One job waits 10,000 seconds, and so on and so forth, right? The expected value is that number, 111,120 seconds. But if and I do this with my students when I teach this class, I say, OK, for $1 million, if I say that's the first 100 jobs, make a guess as to what's going to happen to the 101st job. What do you guess? You almost assuredly do not guess that number. Right? This is a good aggregation, but it does not give you a lot of inference power about what's going to happen next. In this case, the mode, which is the most frequently occurring value, is the one that you would like to use. That's hard to estimate. And so what we actually do is we estimate the quantile. Right? If 95% of the jobs wait 10 seconds or less, I can say, with a 95% chance, if you will, that the next job will wait 10 seconds or less, assuming that that's a random sample. And we can deal with autocorrelation in the future. So the first realization we had is get away from the moments. It's about quantiles. And the reason it's about quantiles is we can make inferences about individual events in very, very widely varying data if we know the distribution. OK, so how does one estimate quantiles? Well, you really want to do this well. It's not enough to estimate the quantile. You actually have to estimate confidence bounds on the quantile, because the quantile is like any other statistic, a statistic, and it has an estimation error. And so what we really needed to do was develop a way to estimate confidence bounds from data on quantiles, time series data. And then we're going to use one bound or the other as a representative of a conservative estimate for the quantile. So if we're talking about the upper 95% estimate, to estimate the upper 95 quantile, we're going to use the bounds estimate. But then you have to tell us how certain you would like us to be about that estimate. And for everything else that comes, the quantile may vary, but the confidence bound on the quantile is 95%. It's upper or lower, depending on whether you're going one side or the other. But if you take that to be conservative, then no matter how bad things are, this should be a statistical guarantee on that event at that level of certainty. You will get at least that much, if not more. All right, so we invented essentially a non-parametric time series predictor, forecaster, out of 3 separate statistical methodologies. Right? We needed a quantile estimator, and when I say we, it's myself, a PhD student of mine, Dan Nurmi, who's looking for a job, in case you're interested, and John Breivik, who's a PhD mathematician from Berkeley, but who decided he wanted to come and work in our group for a couple of years on these kinds of problems, right? And so we needed a way to estimate quantiles from data, and his idea was to use a formulation based on a binomial representation of the data. And I won't put up the actual values, but if you're interested in what the specific formulation is, I'm happy to talk about it offline. Then we needed a change point detector. It turns out that if you're estimating quantiles from distributions and you've got time series, what you really need to do is top your time series up into regions where the distribution is relatively stable. And that's often termed stationarity, although that's a bit of a misnomer. And so we had to invent a way to sort of figure out what the minimum meaningful statistical history was in order to be able to make this estimate. So these 2 things are fairly general. You can take pretty much any correlated time series and throw it at the system, and these 2 things will work together and make a balance forecast for you. But for the actual queuing system, we also needed an online clustering methodology that's model-based, which is not the same thing as these mean-based techniques. And that has to deal with non-first-come, first-serve queuing disciplines, and you'll see why later. But we had to build 3 things. We had to investigate mathematically and then put together 3 separate techniques to make this time series thing to make predictions. OK. This is 10 years of supercomputing. It's about 2 million jobs. And they're from a whole variety of organizations. So NERSC is DOE, Lawrence Livermore National Labs. That's Los Alamos National Labs. That is the San Diego Supercomputer Center, Texas Advanced Computing Center, San Diego Different Machine from the mid-90s. And this is the current TeraGrid. And the reason we took such a wide variety is we didn't want to bias our results based on our methodology, right? These traces existed long before we started. And these are different queues. So these are different queuing disciplines, different priorities. We don't know what they mean. Sometimes the information has been lost, but the jobs were tagged this way. Every time a blue bar crosses a red line, it's a successful operation of our methodology. So while we can't provide you a proof that this works with all the autocorrelations and the other potentially damaging statistical arguments you can make against our methodology, empirically, that's one hell of an evaluation. This technique on legacy data works. And that's the 95 quantile. That's the hard one. Medians are much easier. You can do it with a lot less data. The tails are the tough part. So if we can do the tails, we assert we can do harder things. So now, I apologize. I actually do use that when I give this to the students. From an architectural standpoint, the methodology that we use to do this in real time, and I'll demonstrate this for you in a moment, is sort of morally similar to what we believe goes on at Google. You have a crawl, right? And the crawl basically goes around and gathers up content, which then you archive. And we archive it with something called the Network Weather Service. But you park it. And then you run a bunch of analysis on it to do things like PageRank. Well, our analysis is qubits. And then you publish the results. And you publish it according to a number of different APIs. And so do we. So from an architectural perspective, we've sort of got a scalable venue, a scalable analysis venue for taking now not content, but log data. What happened to the jobs in real time, right? And it's a real-time system, running this analysis on it and publishing the results. OK? And so we do have, hopefully, a number of different interfaces. This interface was done by a student, Ryan Garver, who has gone on to work on Ruby on Rails. And I think if he was a Ruby on Rails programmer when he did this interface, this would look a lot better. So I'm not going to exercise it. We're actually in the process of rewriting it. But what I will do is show you what the NSF supercomputing community has done. So this has actually gone into production at NSF. This is a web service-based portal run at Texas Advanced Computing Center. And it talks to, this is what all the TeraGrid users use, it talks to Santa Barbara, when users want predictions. Now, this is still them. The delay here is not us. That's their resources page. Here is us. Okay? So you can ask questions like, at this very moment, if I have a 16 CPU job and I want it to run for 4 hours, and I want to know what the 95% confidence bound is, this moment, what should be happening, if everything is going to work, is that it goes to UCSB, to our system, computes these numbers, and returns them. So there is a 95% chance, or more, right, because it's a bounds, that a 16-node job that wants 4 hours of runtime will start in the next 26 minutes at Oak Ridge, if submitted now. There's a 5% chance it will wait longer than 132 hours on this machine. And we verify these numbers, right? Part of the reason we did this as a service venue and not as middleware is because it's easy to get this wrong. And there's lots of ways that this can fail, right? Some of them statistical, some of them having to do with failure modes in these machines. So we're constantly analyzing the answers we send back. Okay? Now, this web page is the third most popular web page on the TerraGood user portal. And the other two are the other two pages I just went through, the home page and that first resources page. You cannot get to this page without going through that. Okay? So if you're asking, well, does anybody care? Right? Because 25 years people have been doing this, the answer is they seem to. And I have some data on that as well. OK, so that's exciting. And we did that. And boy, we thought we were smart. You know, we went, wow, we saw this problem, and we have these users and all this kind of stuff. And the very first thing that happened was a group at San Diego called me and said, Rich, this is not what we want. They said, we have a brain imaging application. And the brain imaging application takes 4 minutes to run on 16 nodes of the various supercomputers that we've got. And we need the answer in 8 minutes. Can you use your system to predict whether we're going to make the deadline? Because if the answer comes in 8 minutes and 1 second, it's no good to us. And so we said, well, you want the probability, right? You want to know what is the likelihood, the probability that your job will meet the deadline. We said, OK, we think we can do that. All right, and we'll go back to the TerraGood user portal. And I apologize for the speed with which this thing seems to cycle. And we'll get 2 more hits for those other pages. And then we go to us. And here on the left side, we have invented the following thing. I want 4 CPUs, and I want a runtime of 2 hours, and I want a deadline, sorry. I want to know if it'll start in the next hour. By the way, a lot of this work was done under the auspices of grid computing. If anybody comes to speak to you about grid computing, ask them to show you their software in a demo mode, because this stuff works. And there are the probabilities. At ORNL, that job has a 97% chance of starting by your deadline in the next hour. Purdue Lear, it's only a 35% chance. So we can invert the answer that we give you to make deadlines, or to deal with deadlines. Right, so great. Here's some of the questions that inevitably come up when I get to this point in the talk. Great, what happens if everybody uses this? We don't actually know. We've done some simulations. The simulations indicate that, that the size of the user community doesn't matter. Other things do matter, like how busy the machine is. And less busy is a problem, which I'll explain. But we've taken some steps. And in particular, we don't consider job cancellations in making the prediction. And that is so that users who look at predictions are not able to affect the predictions we make by canceling their job while it's in queue. That's very important. We can make a much better prediction, a tighter bounds than we're doing if we did that, but then it would be susceptible to feedback. And so far, it hasn't been. And then there's this other question about whether user behavior will change as a basis of what they see from this. And we don't know the answer to this question. There's some evidence. It's been running in various forms since for a year now. There's some evidence that nothing is happening. There's some evidence that something is happening. And we haven't been able to tease it apart yet. From a statistical perspective, autocorrelation just freaks people out. And they say, look, this thing is heavily autocorrelated. Isn't this a problem? And it is and it isn't. In some part of it, it is, in the sense that for the change point detector, you need to know what the autocorrelation is to know whether an event is rare or not, based on the fact that it's correlated with other events that have occurred recently. So we do consider it explicitly. It computes an autocorrelation when it does this. But in another respect, it's not, in the sense that we're looking at jobs that go into the queue and predicting them based on jobs that go out of the queue, and the amount of time in between is very, very large. And if you look at the correlation between these jobs and these jobs, it's actually a lot lower than it looks in the time series. So we actually, the binomial methodology is very, very robust to autocorrelation for reasons we only partially understand. And there isn't enough autocorrelation in these two measures to actually confound it. Right? And then the last thing people say is, yeah, well, Rich, you're talking about this like a guarantee. You're guaranteed 95%. And guarantees don't come with probabilities. And my answer is, yeah, but they should. Every guarantee that you are given, legal guarantee or quality of service guarantee or whatever, has a failure probability. The difference is we know what it is, and we'll tell you. And in fact, you can tell us how certain you want to be, and that will affect the nature of the answer. Another criticism, and this came out of one of the reviews that we got for this work, was, well, this is just an interesting party trick, right? Great, you have figured this out, and nobody really cares. And they don't care because you're not actually making a prediction for an individual job. You're making a bounds prediction. And to illustrate that criticism, this is the upper bound. It's 27 minutes. And you know that if you have a choice between that system and this system, you'll wait no longer than 27 minutes with 95% certainty. Great. But if I ask you to compare these two systems, say Pittsburgh and Purdue, and I say the upper bound is 55.2 hours there and 59.4 hours, and I can't tell you anything about what's going to happen before that. There's a 5% chance it'll wait this long, but there's a 95% chance it won't wait that long, and I'm not going to tell you what is going to happen. Is that useful? And I have a lot of users who said, no, that's not useful. It's not a specific prediction. And all the administrators we tried to talk into getting to run this basically said that. Said no one is going to use the bounds prediction stuff. Right? So we have quantiles, but it's a bound. And that bound may not be utilitarian until we started talking to the weather forecasting people. This is a cartoon that depicts, without time scale, kind of how weather forecasting is done. Right? You've got a series of observations, and they're taken periodically, and they may or may not be from sensors that can be controlled. They go through some analysis and some cooking. Right? Data products are produced. Then there are forecasting models. And in the case where these are not dynamically controllable instruments, some information will be fed back into this analysis and assimilation, potentially. And in the old school, this happens over the course of months. It's a very slow process. And so you're producing files, and files are being consumed. And then from that come forecasts that are then given out. At Oklahoma, Kelvin Drogemeyer has put forth the idea that this cycle can be made to run in real time. You have dynamic Doppler radars, and you have tornadoes that are moving across the country. So this is going to not be planetary weather. They call it mesoscale weather. And what you want to do is run a bunch of this and then redirect the radars to know where to look next. And you want the time scale on which these things come through to be rolling forward at shorter and shorter intervals, because if it's heading for Oklahoma City, you want to start getting people out of the city. But it's very, very expensive to have false positives. So these guys want to launch based on a static Doppler radar picture, on-demand, high-performance computing, and to keep doing it in this cycle. Right? OK, so that's hard to do if you have 7 orders of magnitude variation. But it's also hard to do for these other requirements. The first is that you can't go in and change the codes. Before I started this work, my specialty was building these highly adaptive, high-performance codes. I would spend years engineering these things, and they would be able to move themselves and shape themselves. And I said, give me the code. I'll do that to your code. And they said, you can't touch it. It has numerical properties that we have spent years verifying. As soon as you start playing with the data structures, we have to go through a re-verification step, and that's going to take a long time. Forget it. You're stuck with these codes. So again, there's this long cycle. And so for good scientific reasons, you have a lot of man-years invested in this. You have an incremental and sedimentary code base, and a build model that expands but never contracts. So even just building the code is hard. The second thing is you're dealing with users who are not very tech savvy. I suspect that a lot of the innovation in the commercial sector is driven by people who are very excited by the technology and what it can do for you. And that does not describe, typically, hard scientists in this space. Fortran is a good tool. MPI is an OK tool, depending on who you talk to. It used to be a really, really bad word. The web is just kind of puzzling to many researchers. Anytime you start talking about a network, you start making them angry, and forget grid computing. Grid computing is basically sort of a formal way of doing this, and it's a bad word in many of these contexts. So you're constrained in the solution technique that you're going to be able to use here. Nonetheless, what Kelvin and his colleagues had done was to try to present this code as a workflow. So they're going to wrap the legacy pieces, link them together with BPEL, which is a language, a scripting language for doing this, and then run them on dedicated machines. So if there's an emergency, they have a stockpile of clusters that are just waiting to run these things. And they've gotten the national centers to implement preemption. So if Katrina is going to happen, or they think Katrina might happen, away you go. But there are a lot of non-emergencies, right? You need to do development. You want to experiment with the models. You just want to know what the weather is going to be. And here, what they want to do is to make reservations. They want to say at 6 p.m., we want to run, and we know how long we're going to run for, and we know how much space we're going to use, and we know how often we're going to do this, because these experiment cycles are fairly well understood. And hence the problem. When you start allowing users to make reservations, you lose utilization, because you're blocking out those resources, and the users, they use them, but the resources are completely gone. So there's a loss of utilization that has to do with reservations. And furthermore, the weather people are not the only people who want to do this. If everybody's getting 7 orders of magnitude variability, a reservation sounds like a really good idea, even if you're not predicting the weather. And so as soon as you put this into place, there's this huge fight. And the centers don't want to be the arbiters for this. So this was the state of play in 1993. And one of the first things that I was supposed to do while I was at San Diego as well. And there have been a lot of different approaches put in to allow this, and none really made it into production. Currently, you can make reservations, but it's done by hand. It takes weeks or months to set up. It's usually only available to a few users. You can do it, but you have to justify when you're doing it. And really, the only justifications are you're doing a demo for your funding agencies, or there's an emergency, or there's some big event. And they're usually manipulated by hand. This is actually changing a little bit, partially, I believe, in response to the work that I'm about to show you. But the bottom line is there's not an automatic method in place that is generally available. And I came across this while working in the context of a large project that had been run for many years by a number of high-performance computing luminaries, except for that one, who were working on trying to figure out what programming abstractions we needed to give scientists so they could do this kind of thing more easily. And what we decided to do in that context was to try to see if we could use this predictive technique to build what looked like a reservation, but was really a statistical party trick. And that project was called VGRAD. So we worked on that, and we worked on it for a while. And we were staring at graphs like this. And here, this is the previous graph I showed you, but I've superimposed the upper 95% quantile, right? And you can see how it moves. And we were staring at that, and one day I realized the width of that is 1 month. This doesn't look all that stable, but if you zoom in, it's really pretty stable. That's a month, right? So what this means is if I make a prediction now of the upper 95% quantile, it's good for a while, maybe several days. That's good. That means that the distributions are stable. Even though there's a lot of variation, we're not going through change points every 5 minutes. And that's what you would expect. Next thing you need to know is how it is, a little bit about how it is that high-performance computing scheduling works. And the important word on this thing is backfilling. Basically, if someone wants to use a large fraction of the machine, because it's space shared, you have to drain some number of processors, which essentially means idle them. If I want half the machine has to be idle in order for me to take advantage of it, and it doesn't go idle all at once. Processors basically die at their own rate. So, and so while those processors are idle, you're losing utilization. And so somebody at Argonne came up with the idea of saying, well, wait a minute, we're going to make our users tell us what the maximum runtime is for their jobs, and we'll backfill into the idle deadline to get the utilization back. And there's two kinds, conservative backfilling and liberal backfilling. But what this does is break first come, first serve in a very nasty way. Because now there's this game theory. How big a job can I slip into the backfill? And users constantly play with this. And so centers constantly adjust the knobs. Sometimes those knobs get turned 3 or 4 times a day. Right? So what you've got is this kind of game between users that are trying to run their short jobs in the backfill, right, and centers that are trying to keep utilization as high as possible. And that's what causes all of the difficulties. But if it's relatively stable with respect to the quantiles, we made the following observation. We said, well, OK, let's say we want a 1-hour reservation that starts here and ends here, and we have an infinite allocation. We don't care how long we actually run for. We just need to be running during that time slot, because that's when the forecast is necessary, right? And this is 12 hours into the past, or more appropriately, this is now, and this is 12 hours into the future. We want a reservation for 12 hours from now. Well, if we submit a 13-hour job, which covers 12 hours of potential wait time and 1 hour of run time, and it starts any time before that time, we make the reservation, right? It's 13 hours. It might start immediately, in which case we burn 12 hours of allocation. It might start right here, but if I know the probability, right, I know the probability of making this reservation. But if things are stable, if I wait an hour and submit it, now I only have to submit a 12-hour job, and so on and so forth. Notice what happens about here. That's where backfilling occurs. At some point, your job gets short enough that you get backfilled, and the probability of making your deadline goes way up. And that is a consistent effect. It's not an effect that occurs in exactly the same spot, but all of these systems use backfilling. So in some sense, statistically, we can reverse engineer where the backfill is at any moment and delay your submission until the latest possible moment that meets your probability target. So let's say you want to be 75% certain. You want a 0.75% or 0.75 probability of making your deadline, and or better, right? All we have to do is compute this trajectory, which we can do online very, very fast, and then walk the schedule backwards to find the first place where the trajectory crosses the 0.75 line, and that's where we're going to submit your job in the future. OK? So user specifies a reservation start time, a node count, how many nodes, how long the job is going to run for, what the reservation time is, and what the target probability is. And we compute when to submit that job in the future, if there's a time in the future we think we can submit it, such that you're going to make that reservation with the target probability. And here is one set of results. We've done this a lot. On the NCSA Terragrid, fully production, same sort of, it's actually worse than the data I showed you. 12 hours from now, 16 nodes, 1 hour, 75% probability. We submitted 356 job requests over like a month and a half or 2 months, something like that. There were only 257 jobs that actually got submitted, which means 99% or 99 times the system came back and said, I can find no time in the future such that you're going to meet the 75% probability. But of 192 slots that were successfully acquired is almost exactly 75% of 257. We were off by 1. That is a miracle, right? Because we made a reservation on that system that doesn't support reservations, that has that level of variation at the target probability we wanted to make it. We've tried this for a big collection of jobs and machines and times. And these are the numbers. That's a conservative estimate of 50. That's a conservative estimate of 75. We didn't quite make it here. And this is instructive because it's one machine. And it's one machine that has a non-statistical behavior. And it turns out that if you want to do this trick, you've got to be able to detect that. And I'll talk about what we're doing about that. We'll talk about future work. OK, so in general, with maybe a little bit of an error that we think we understand, this works. And it doesn't require the centers to lose any utilization, and it doesn't require them to re-engine their system. In fact, they can't stop us from doing this. They don't know the difference between a job we're submitting under this job's control and what a user's really doing. It's an overlay. Okay? Now you say, well, Rich, how much am I paying in terms of allocation? And I ask, well, what did you pay for your reservation slot? And they say, well, each of the centers charges me something different, and they change the charging, and I don't really know. And I say, well, I'll tell you, on average, you burn 1.19 times your actual runtime if you want a 50% target probability. It only goes up to 1.22 at 75%, but it's fairly substantial. You're going to double your execution rate if you want to be this certain about a single job. So there's a cost, but it's quantifiable, and it's your cost. And it's not set by the centers based on some non-economic thing. It's purely a function of the demand on the machine. So we think that that's an attractive property. OK, let's say you don't like 75%, but you're kind of fond of the 1.22 number. Well, since we know what the failure probabilities are, if we're willing to assert that the failure probabilities on two machines are independent, and they look very, very independent, you can start combining them. And in particular, if you combine 3 of them, and they each have a 25% chance of failing, the chance that they all fail is 25 cubed. So the chance that at least one succeeds is 1 minus 25 cubed, which is 0.99. But because we cancel the other jobs, your allocation cost is 1.22. And we just now made what looks like a fairly reliable reservation at a very small extra cost through replication. And we run actual hard reservations. They're not this reliable. If you make a hard reservation, there's a probability it's going to fail, and it's not 1 in 100. So we think we've solved this problem. And we think we've solved it very, very neatly using statistical techniques. And if you don't like the probabilities that we're getting, as long as we have enough scale, as long as there are enough machines that are operating independently so that we can make these decisions, we can boost the probability up to you want. But what you sacrifice is you don't know which machine we're going to run you on. It's a virtual reservation. The resources are virtualized. OK, so we brought that up, and they said, well, we're not interested in that. We're interested in co-allocation. Co-allocation is where you're going to get a reservation on 2 machines simultaneously. And this is of dubious use in a production setting, but it's very, very useful if you're trying to experiment with scaling factors, right? And so the centers are very resistive to this because it's even worse in terms of utilization. It started showing up as a demand in 1996, and last year NSF, the people who essentially allocate the funds for this, mandated that co-allocation will be supported. Can we do that? The answer is yes, but it's tricky. And in particular, the joint probability goes like the nth root, if you have n resources in your co-allocation, up. So in particular, if you want a 95% certainty of 2 reservations meeting the deadline, each one has to have a 0.975 probability of success. And as n gets bigger, that number gets bigger. We then need to think about how we can find probabilities of arbitrary size, but this probability boosting thing comes to your rescue, right? If I had 6.75 reservations to make, VARC, by the way, is what we call this, virtual advanced reservations for queues. If I had 6 of them, and I can break them into 2 groups of 3, each of one is 0.99, the co-allocation probability is 0.98. We can do co-allocation. No changes to the centers, no loss of utilization, no screaming and yelling. OK, I'll start to finish. Where are we? Qubits. That's basically the predictive methodology. And it's the thing that gives you the bounds. And it consists of 2 general pieces, the time series, the binomial estimation part and the change point part, and a third piece which is specific to the queues. It's ending its first year in beta release, the site is. It's been supported in production, full-on TeraGrid production, since January 1st of this year. And in the last year, we've been doing about 3,000 hits steady state per day. We went through 2 months where we did like 100,000 hits a day. And what was going on was a couple of groups got so excited, they thought we were going to take the site down, and they were scraping our web page. And we finally explained to them, you know, we're going to keep it up. We've got the data. And so this is really our steady state, about 3,000 hits a day, about 100,000 hits a week. This is from a user community that's between 3,000 and 4,000 in size. So that's a pretty good hit rate from such a small user community. VARC, the reservation mechanism, is in alpha release. It's ready for beta, but we're getting a lot of pushback from the centers. They don't really believe that this stuff works. And so we're going through a very extensive evaluation period at this moment. And co-VARC, the co-allocation thing, if they're not happy with VARC, they're really not happy with co-VARC. And here I think their unhappiness is justified in the sense that when we do these co-VARC things, we're seeing failures not in the statistics, but in the actual mechanisms we use to launch the jobs and reap them. And we can't tell if there are failures or failures in the underlying systems. The failure modes in these machines are nasty. And when you start combining them, particularly in this way, it doesn't look to us like this is working yet, but we think we can understand it. OK? There's a couple of open issues. One is statistical. It turns out that light load is a problem. That sounds weird, because if the machine is lightly loaded, you sort of know what's going to happen. But one of the things that users do when they see a lightly loaded machine is they submit an unreasonably large number of jobs simultaneously. Now, this is not good from a center perspective. You bought this big machine. You want users to run jobs that require more than one node at a go. But a lot of users write scripts that submit thousands of single processor jobs, using it as a big cluster. We can't stop them from doing that, although we try to discourage them. But the problem is, if you can corner the market on delay, if you can influence by yourself what those 7 orders of magnitude variability is going to do to your job, we can't make a statistical prediction. It's not a statistical problem. Right? And so, so we need to actually filter for this. And we've experimented with one filtering technique, and it works in many circumstances, but I'm not satisfied with it. I think we can crack this problem in the next 6 months. The second problem is really a cultural one. And this is where I feel much more akin to you all than my colleagues, in the sense that administrators, and these are system administrators or administrators who hold the purse strings, are just not comfortable with the idea that their big, expensive machine needs to be treated phenomenologically. What do I mean by that? I am doing an analysis of what the thing does without explaining why it does it, like you do PageRank. You know, you figure out what's the right page. You don't really know why it's the right page. You just know what to look for to know that it's the right page. Well, that's what I've done, right? There's a phenomenon out there that I am studying automatically with these methodologies. And these people, their response is, no, we own the machine. We control it. It's not a statistical problem. It's a mechanistic problem where we're just going to fix it. And my response is, well, I've been waiting. And the users have been waiting. And if you can do it this way, you should do it this way. But I think their arguments, I understand. I'm sympathetic to them. Right? It feels weird to be doing this. Here's some lessons that we think we've learned. And this first one may not sound unusual to you, but sounds very unusual in my community. It's really possible to use online forecasting to build useful services in dynamic environments. Now, I've been doing this in this context and other contexts for a while. And a lot of people just said, look, this is purely an academic exercise. You're never going to be able to build anything that anybody's ever going to want to use out of this stuff. And they just turn out to be wrong, dead wrong. But I will admit, my first 100 attempts at this problem failed. Right? I worked on this problem for 10 years before we started to crack what was going to work. And I did, and they failed for the same reason everybody else's does. You just don't want to use a moment-based approach. Right? It's really, really difficult to make inferences, and variability kills you. Another lesson, which I think is interesting, at least for our community, is that this notion of combining services in an overlay, which we talk about a lot, right, really requires two things. It requires a success probability to be associated with each service, and one that you can rely on. We talk about success probabilities, but if you actually measure them, you need something hard here, and you need scale. And this is a real eye-opener. Scientific computing people, HPC people, think of scale as the enemy. The larger things get, the more likely they are to fail, the larger the latencies, the more the variability. It's not your friend. And they're just wrong about that in this context. The more machines you give me, the more I can ensure independence, the better job I can do. Right? Those numbers come from about 15 machines, which is really what the NSF is funding in production at the moment. There's about 30 machines, but only about 15 get used seriously. You triple that number, those numbers get way better. Okay? Another sort of controversial statement, and this is one that I missed until we did this, is middleware is not the best approach. Now, For a long time in this discipline, we were talking about this software veneer idea. It's really an operating systems idea, where you're going to put a service layer on top of everybody's operating systems. But if you do that, and you do that at least for monitoring systems, you don't get the data you need. The data has to be good. And the reason you don't get the data you need, I think, is because there's kind of a conflict of interest. So we originally put the software out as middleware, and a bunch of people stood it up and they said, well, our machine looks lousy. We're just going to change the probability numbers. And so suddenly their numbers looked really, really good, but our experiments were failing. And we're like, what are you doing? And they said, well your 0.595 number looks really bad, so we made it 0.2. I'm like, well, don't make it 0.2 because we can't make inferences from that. And they said, well, but it's making it look bad. So if you put the monitoring software out there, people are going to manipulate the monitoring software for their own reasons, and those reasons are not necessarily your reasons. And so at least for monitoring, I'm fairly confident in this. For service composition in general, I think it's an open question. And that's because there are a lot of complexities involved with things that are not just sort of scraping the data and making an inference that may come up to bite us. Okay? In the remaining time, what I thought I would do is then try to draw some parallels between this kind of research, which ordinarily, at least in my discipline, we don't think of as having much to do with what you do, and what it is I think you do, right? And so the first similarity I'll say is, this is a different kind of computer science research. This is not the kind of computer science research that typically gets published in systems journals, and it's because you've got to work with real users. None of that happens unless they're real users and real data in real time. And that's really hard. If you're an academic, intruding on someone else's work cycle so that you can verify some theory requires an awful lot of machinery that my competitors do not need to build. And you sort of experience this as well. If you go in there and you tweak something on Google and it gets 20% slower, like, governments topple, right? I mean, you're like a national resource now. And I expect a law that says Google response has to be 27 milliseconds or someone goes to prison, right? Okay, or maybe not. So really working with users at scale is a big challenge, and it's really a challenge for computer scientists. And it's very hard to reconcile that with the incentive systems that are built into more academic computer science, but I think we need to. Second similarity is that this notion of scalable service venue, where essentially you take the data, you manipulate it, you look at it, massage it, and make sure it's what you want it to be, and then publish the results, is really the right model, right? And that's, we didn't think it was going to scale. You've shown that it can scale. And really the community, I think, needs to just come around to that, and I think they are. And the last similarity is, this is really a triumph of applied statistics, and so are you, right? From systems builders' perspective, we don't trust statistics. And in Google's case, you're looking at content, and we systems people can say, well, but that's the content. The machines, we understand the machines. No, in fact, applied statistics work great for machine performance. In fact, in some sense, they work better than for content because machines behave the same way over and over again, typically. So, and also, and this is true for you guys as well, the results get better with scale. I think that's a key result. But there are some differences. The first is that there's an incentive mechanism based on the use of these systems which doesn't exist for you, and which some people argue is just broken or, at the very best, counterproductive. I don't want to argue one way or the other. I'm just saying that this is an assertion that you can make and I think defend, and I think it needs to be studied. And also, we have a huge legacy problem, right? We can't make a sea change in any of this without potentially obviating a huge investment that can't be recovered. So you need to be very, very cognizant of legacies in this space if you want to do this research. OK? What do we have planned next for this work? Well, we're going to try to expand the model. We're going to try to say, OK, why don't we set up our own job submission site? And if you trust us, or you're willing to give us a proxy certificate or some other magic voodoo, you can send your job to us, and we'll run it for you. And we'll run it for you cheaper and with better response time based on where you're entitled to run. Okay? And the reason I think this is going to work is because it separates these concerns again. The centers are concerned with utilization, and we're concerned with getting your job done fast. And because we can focus on that, and they can focus on utilization, I think we can meet in the middle. From a Google perspective, this is sort of YouTube for jobs in the sense that you're going to upload your job to us and then potentially get back what you want. I don't know, it's a bad analogy, but we think of this as opposed to just giving the information. We're going to take responsibility for the job. And that introduces complexities, particularly with respect to legacies that we really need to study. Another thing that we think we can do is we can predict the availability of services themselves. So now we actually know what's going on with the queues. There's a tool called Grid FTP. Grid FTP, depending on configuration, can be reliable or unreliable. Very first thing the people from North Carolina said is, well, can you do the same thing for Grid FTP? Can you predict whether my Grid FTP is going to work or not? We think we can. Right? We've actually done it for machine availability. We monitor the labs at UCSB, the student labs, where students routinely reboot the machines. We make phenomenally good predictions about how much time you're going to get before that machine reboots. Phenomenally good, startlingly good, in fact. And the last thing is, you can think of all of this as QoS for dynamic environments. This is where we're going. Before I say thanks to everybody I need to say thanks to, I just want to take this opportunity to say that we lost a visionary in this field in Ken Kennedy last year. If you don't know who Ken Kennedy is, he's really the person who has been driving a lot of the thinking in compiler and runtime system work for high-performance computing over many, many years. And the VGrads project was initiated by him. Before that, there was the GRADS project. I've been tremendously fortunate to work with Ken, and personally, I miss him tremendously. And I'll end here by saying thanks to NSF, not only for funding this work, but for just giving me access. Right? A lot of this is being able to look at the logs and make inferences about what's happening. The centers, I mean, I may have portrayed them as an adversary, and in many respects, or at some levels they are, but in terms of giving us access and helping us do this work, it is absolutely impossible to imagine doing it without their cooperation. They really are interested in what we're doing. They're just skeptical about the results. This is my lab, the Mayhem Lab. And I'm just going to plug my students. Dan Nurmi, again, looking for a job. John Breivik at Cal State Long Beach now. Graziano Bertelli, who you cannot have. Matthew Allen, just about to graduate, are all folks who worked at some time or are currently working on qubits. We have a sensor networks effort. It doesn't sound like it's related, and it's a whole other talk as to why it is that's going on. You hired Ye Wen at Google Kirkland from this project. He's very happy there. And I've got two more excellent students who are working on that. And then in the utility computing space, we're spinning up an effort. Lamia Youssef, who will be graduating this year, Sriram Rajagopalan, who is brand new, and Dmitry Zagorodinov, who is my postdoc and will be out. And then I mentioned a little bit about incentive systems. You really do have to think about that, and I have a student, Andrew Mutz, who's extremely excited about that work. This is me, and I thought it would be absolutely remiss not to end with a gratuitous mashup. That is where we're doing our hits today. We did 2,319 since midnight. The one thing I'll say, and this is another interesting research problem, is a lot of these hits come through the TerraGrid user portal in Texas, and we don't know what the IP address was that actually initiated it, because it's being proxied. So a big proportion of our traffic looks like it's coming from one place, but that's the Google Map rendition, and I'll stop there. Questions? Zoran.
So I have a question. So here, like jobs that we are running are different classes. You know, one class will be bad jobs, which you kind of mostly talk. You know, then we have a real-time jobs, like this, or run more like a service. We have development jobs, which can crash any time, and then we have, like, let's say, production jobs, like which have higher priority than the others. So what's the situation in the grid computing, or like about that?
Right. So the way that's typically handled is each resource supports multiple queues, and the queues have different resource limits. So, for example, almost all of the NSF centers support what they call an interactive queue, or a debug queue. And the idea is that your job can be no bigger than, say, 16 nodes and can run for no more than 10 minutes. And you can submit to that queue. And we use that information. We predict for each queue. So we'll give you a different prediction for your interactive queue than we would give you for your standard queue, right? Or a premium service queue, right? Premium service queue, they charge you more for your allocation. So instead of a 1-for-1 occupancy, they might charge you 1.5 to 1. But in theory, your job gets out of the queue sooner. So there's a queue breakdown. And then within the queues, the hidden, so that's published, right? You know what the queues are on the machine. But what you don't know is where the backfill is. That's hidden and it changes. And so we use the clustering technique to recover different service classes automatically. We determine how many service classes there are and what the boundaries there are automatically, constantly, for each queue. So we can figure out if your job is a 16-node job and it's going to run for an hour, it goes in this service class in that queue. But if you were to submit it to this queue, it would go in that service class. And we make 2 different predictions.
But it's still like bad jobs. So.
Bad jobs.
Batch.
Yes. Oh, I'm sorry.
So I mean, the point is I cannot reserve it for the next 2 years, like
nope.
Fly machine.
No, this is all batch. Okay. These machines, again, are run entirely in batch mode. You might think that that's unique to the centers. I got a call from an oil company. I won't say which oil company, but an oil company, about 3 weeks ago. Batch is popular. That's all I'll say.
I have a couple of questions which are like
thanks for coming.
No-wise questions for high computing, high performance computing.
Sure, absolutely.
So you mentioned somewhere there are only like 30 machines that the NSF has provided and your measurements are from 15. So I'm just trying to understand because from my perspective, the machine is very small. Are these, what kind of machines are
Yeah,
these?
good question, sorry. Great question. So at the moment, there are approximately 30 scientific instrument class machines. And that's a very broad category. So a good example is DataStar. Probably one of the most useful machines to the scientific community is San Diego Supercomputer's DataStar. It's an IBM SPXX with the RS6000 based processors. It has 256 nodes, and each node has, I think, either 4 or 16 processors. There's some fat nodes that have 16 processors, but most of them are 4 processors, and they share memory. And then the interconnection switch is this very, very fast federated switch, which is very low latency. Okay, so there's DataStar, there's Blue Gene. What a lot of people have been doing, Eldorado, which is the Cascade memory system and the AMD processors. So one class of machine, I guess, is commodity processors hooked to some fancy switch. And these things are big. They tend to be thousands of nodes, not tens of thousands of nodes, but thousands. There's another class, which is very, very large clusters. So the NCSA Teragrid node is 1,000 IA64 dual processor cluster nodes and MirrorNet. Tsubame, we actually run in production. The one outside US system unit is Tsubame. Tsubame is the fastest supercomputer in Japan. It's faster than the Earth simulator. It's a bunch of Sun processors hooked together with InfiniBand, and we're running on that system as well. But they tend to be very large resources that you log into, and they're only housed in places that have sort of the maintenance facilities necessary to keep them running.
So what I understand is the machine that you mentioned is pretty much like a cluster that we talked about.
It's kind of like a cluster, yeah. I mean, you know.
Very tightly integrated.
Logically, it would look like a cluster to you, right? I mean, it would look like a shared memory cluster where the nodes potentially can share memory, and multi-core is blowing that all up, right? I mean, there's going to be a lot more shared memory at each node, but yeah, that's exactly right.
The jobs that are submitted are like, do people submit jobs to like multiple of such machines, or they submit?
Well, up until now, the answer to that question has been no, but I think that's what's turning people on. Because you were given an allocation on one machine and not on another. And no one knew how long it was going to wait. But as soon as we put this up, or maybe, you know, coincidentally, NSF changed its allocation policy. You get what's called a roaming allocation, which basically means you get to run on any machine you want. And as soon as that came out, I think our hit rate went way up, because now people actually have a choice. But the architectures are different. An IA64 is really different than the RS6000 in terms of granularity, and your codes have to be built to port, and not everybody's codes are. So it's not a completely fluid decision-making field. Good questions. Yes, sir. Hey, Bill.
Are you worried at all about the effect with the co-location scheduling, where you submit multiple jobs, but you really only plan to run one of them, the best one that gets scheduled? Are you worried about the effect of canceling?
No. Well, OK, so
on the
we're not worried. Should the centers be worried? The answer to that question is probably not. OK, so this is a deep question. The question is, if we're going to do replicated submissions, and then one pays off and we cancel the others, what effect does that have?
Mostly on the data, the statistics that you're trying to collect,
Right.
does that sort of negatively impact?
No. And the reason is because we don't look at any jobs in queue. If you cancel, we never see the data for this reason. We've actually experimented with what would happen if we looked at data for in-queue jobs, and the predictions get much better. But there's this risk. However, you might ask, well, gee, if we're prompting a lot of cancellations, or we're doing, does that affect the individual schedules in the backfill? And the answer is, we don't think so. If you're doing conservative backfilling, from a theoretical perspective, it might. We ran 1 billion simulations, and we couldn't make it happen. But theoretically, it could. If you're doing liberal backfilling, though, not going to affect you. I don't think. Sorry.
So, but what is the overhead of actually running your job? Because like, where is the data sitting for the job and so on? Like, how do
Yeah, that's a good question. So, question is where's the data and what's the overhead, the startup overhead? And that depends. There are some jobs where you have to move an awful lot of data, and so the data gives the job an affinity to a particular machine. That's true in a lot of cases. But there are some jobs for which the data movement's actually pretty quick. And a lot of data in this space is kind of different. So there's a 40 gigabit link between San Diego and NCSA. You got to have a lot of data before 40 gigabits on a 3-hour run isn't going to get you, or gigabytes isn't going to get you the data there. But there are some jobs for which that's true. However, what we have found, particularly, now we're working with the urgent computing people. There are these people who are worried about disasters, right? The emergencies. And they want us to be able to predict something called next to run status. So all of the centers agree to not kill, but essentially put whatever job comes from them at the head of their queue if they present a particular token. And one of the questions you could ask is, if I had such priority, how long would it take me? So we can actually predict that for them, right? But they have a staging problem. They need to stage the data. So one of the questions they asked is, well, could you predict the lower bounds on the file transfer time? And it bounds is what you want. You just need the data to arrive before the job starts. You don't need to know when it's going to arrive. We can do that. Now, whether it's independent or not, I mean, we're not doing it. And it's because another feature of working with real users is don't get it wrong. If you put it up and it's wrong, you will never do it again. So it takes us a long time to do these things, because we spend a long time convincing ourselves this is going to work, right? And I mean, I have had these moments of utter depression where I thought, this is never going to work. It's never going to work, right? I mean, I'm just looking at it going, it's never going to work, because if we get it wrong and it doesn't work, we're dead. I'm glad I was wrong. Other questions? You're all immensely patient for coming to listen to me yell at you today, and I thank you tremendously.